In this video, we're going to be talking about stacks as a data type. In particular, we're not going to be talking about how to implement them yet. Implementation is going to be a separate video. This video is just about sort of what stacks are and how we use them in different situations. So what is a stack? So a stack is a data type that stores a collection of elements, and we don't necessarily know what type of element this is, right? Like with linked lists, we didn't know necessarily what it's storing, but the concept of linked lists is a collection of elements. And here, in a stack, we have sort of two properties that allow us to interact with the stack. So the first is push, which puts an element E on the top of the stack. Pop returns and removes the top element of the stack. And those are the sort of two requirements of a stack. But in a lot of times, people who implement them will sometimes give you some extra functionality that allows you to do a little bit more with the stack than just pop and push. So the first thing is checking if it's empty, right? So you can sort of emulate this using the pop function. So if pop returns, say, null or -1 or some sort of null value, then you know it's empty. Get length tells us how many elements are in the stack. Again, this is not necessarily, not always necessary, but a lot of times it's implemented for you. And then, of course, peek. So peek allows you to look at the top thing on the stack without actually removing it yet. So for instance, a push onto this stack on the right, so this stack has 3, 10, and 4. A push will take -3, and it sort of takes it and pushes it down onto the top. So now we actually can't access 3, 10, and 4, right? Before, we could only access 3. Now we can only access -3. And we can do that if we do have peek implemented. We can either look at it or we can pop it off the stack. So given this stack pop, all it does is it takes that top element and returns it to you. So here it's -3, and it pulls it out of the stack and returns it to you. So those are the two main operations of stacks, and sort of what we might do with them. So it's sometimes you hear the term LIFO for stacks, which stands for last in, first out, right? So the last element we put into the stack is the first one we take out, right? So you can think of sort of recursive calls. Recursive calls push the function, the calls, onto a stack. The most recent one that was called is the first one that's returned, right? And then you keep sort of pulling the calls right there. When you make a recursive call, the current instantiation gets pushed onto a stack. That might be helpful to some of you. If it's confusing, then forget I said it. So some people find it to be a useful way of thinking about recursion, and others find it just confusing. So let's go through an example. So here's an example problem. Consider you're given two stacks that contain a set of integers in a sorted order. So I happen to have sorted them somehow, and I'm going to give them to you. And I want you to construct an array that contains all of the elements from both stacks, but in sorted order. So this should sound somewhat familiar, especially after the most recent lab where we were dealing with, that's right, merge sort, right? So how are we going to solve this problem? Well, to solve this problem, we're going to use this little algorithm here. Again, we're given our two stacks over here on the left. The first thing we're going to do is create a new array that's large enough to hold everything and an index variable. And then we're going to use our peek function to determine which of the elements is smaller. We're going to pop the smaller one off, insert it into the array, increment the index, and sort of keep doing that until one of the arrays is empty, until one of the stacks is empty, and then sort of empty the non-empty stack, right? So Let's look at this first one. Create a new array large enough to hold all of the elements in both of the stacks. How are we going to do that? Well, it's an optional method, but in this case, we would need our stack object type to have this size, to be given the what we called it before, the get length, right? Sorry. So in this case, we need get length, right? And the length of our array is just the sum of the length of A and the sum of the length of stack B. So assuming that we have get length available to us, we can make that array. And then we're going to make some index here. I'm not giving it a name on purpose, right? But it points to the beginning of our array. So we're going to use peak to tell us which of these two is smaller. And it tells us peak on the first one gives us -1, peak on the second stack gives us 0, and -1 is lower than 0. So stack 1 contains our lowest element. So what are we going to do? We're going to pop the smaller element out of stack A, so it no longer exists in stack A. And we're going to put it in the element that our index points to, right? And then we're going to increment that index. Then it says the next thing you're going to do is repeat steps 3 through 5 until one of the stacks is empty. Well, we go back and we peak, we peak at 5 and 0 is smaller, right? So now stack B is smaller. So we're going to pop 0 out of that stack, put it into the index where we want it, and increment the counter. Increment the index. Do that again. 5 is smaller than 6. So we're going to pop 5 off, put it into our array, and increment our counter. We're going to pop 6 off, put it into our array, and increment our counter. Pop 8 off, put it into our counter. We're going to get to a situation where, 10 and 10 are equal. So what do? Which stack should we pull from? Does it matter? No. It doesn't matter which one we pull from. So let's say we pull from the left one, from stack A. So we pop off the 10, put it in our array, and, well, it skipped ahead somehow. So 10 ends up being smaller in the next iteration, so we pop it off and move over. We do the same thing with 17. 17 was smaller than 18, so it gets pulled out and put in here. But now, one of the stacks is empty, right? Stack A no longer has anything in it. So can we compare, can we peek at the top element of stack A? No, there is no top element, right? So now we have to go to our step 7, which says pop the elements from the non-empty stack and insert them in order, right? So we pop off 18 and put it in, pop off 19 and put it in. And now both of our stacks are empty. We've pulled everything out of our stacks and we've put it into our array. And guess what? That array is in sorted order, right? Because these two stacks were in sorted order, now our array is in sorted order. So this is actually how we do merge sort with stacks. And you've sort of already been doing merge sort in this manner, but you've been leaving stuff in the stacks, right? When you pull things out of the array, all you did was, so you had -1, 5, 10, or 8, 10, 17, right? You had a pointer that just sort of moved down the array. Now instead we're actually pulling them off and they're no longer there. But you've sort of been implementing stacks already. We're just going to go a step further and actually sort of use them as stacks rather than in the manner that we had used them before, right? In the next video, we're going to talk about implementing them. The book talks about implementing them in linked lists. So I'm going to do a video on implementing stacks in arrays, and we will go from there. All right.